In 2017, astronomers saw the first interstellar object passing through the solar system, Oumuamua. Yeah, I'm sure you're familiar with the name. And then just 2 years later, the second interstellar object, Borisov, was detected. Oumuamua was unlike anything we'd seen in the solar system, while Borisov felt like a completely normal comet, the kind of thing that we would expect to see. And yet both were on trajectories that clearly showed that they had come from outside the solar system, were just passing through, and then they were on their way back out to explore other parts of the Milky Way. And this gave us a sense of just how many of these objects there are passing through the solar system. And we get this tantalizing possibility of a way to understand the other star systems in the Milky Way, because they could be hurling their comets and asteroids in our direction. What can we learn from this? So my guest today is Dr. David Jewitt, and it is like an understatement to say that Dr. Jewitt has been just an absolute anchor in our understanding of the outer solar system. He was on a team of people that found the first Kuiper Belt object beyond Pluto and Charon, and has gone on to discover dozens of other objects in the Kuiper Belt. And he is working on a textbook that explains the current state of interstellar objects like Oumuamua and Borisov. And so I thought this was the perfect opportunity to reach out and chat with him about our current understanding. What did we learn from these interstellar objects? Where do they come from? How can we learn more about the population that are out there, and the staggering number that might actually be passing through the solar system at any given time? So enjoy this interview with Dr. David Jewitt, a professor of astronomy at UCLA. David, give me a sense of how astronomers first reacted to the realization that this, what looked like an asteroid or comet moving through the solar system, might have come from outside the solar system.
Yeah, I think, a little bit of disbelief mixed with a lot of excitement, I think. So
Yeah.
Objects like that have been thought about for many decades, really. People expected to see interstellar objects coming through the solar system. The question always was, how frequent would that happen? How often would you see one? And the predictions in the literature really are all over the place, from, we'll never see one, you got to wait 1,000 years, to, as soon as we get a big telescope that can survey the sky, we'll see them every year. So the truth is that the predictions were kind of useless, as is often the case in astronomy. And so having one was a bit of a shock. Having one that we couldn't really, question was a bit of a shock.
And with Oumuamua, like, its behavior and structure appeared quite different from, I think, the kind of object that people would be expecting to see. Like Borisov, no problem. That's totally normal. But Oumuamua was a pretty weird object to see as the first interstellar object passing through the solar system.
Indeed. So the basic idea that people had in mind, and sort of still have, is that the parts of the solar system that are most likely to get flung out to the interstellar medium are the distant parts. They're far away from the sun, so the gravitational binding energy, as they call it, is less, so it's easier to kick them out. And so that's probably true for other stars as well. So the expectation is you'll be losing things from the outer parts of planetary systems all through the galaxy. But we know that once you go beyond a critical distance, the so-called snow line, objects tend to be ice-rich. So water ice and other ices can just be frozen out as solids. So those are the things that we call comets. So the expectation was that when we see some interstellar body thrown out from the outer regions of some other planetary system, it's going to come in, it's going to get warmed by the sun, and it's going to look like a comet. And one of the big deals with Oumuamua was it did not. It looked like, kind of boring, but it looked like an asteroid, like a point source, with no hint of a coma and no hint of a tail. And then when people put limits on the amount of mass that it could be losing, the limits were ridiculous. It's like less than 1 gram per second in micron-sized particles. So very, very, very tiny amount of material would have been seen in our data, to produce a coma or a tail, and we just didn't see anything.
I guess what was the clincher then that said, okay, this has to be coming from outside of the solar system?
Yeah, so the defining property is based on the orbit. And so if something is bound to the sun, its orbit is going to be an ellipse around the sun. So the eccentricity is going to be less than 1. If it's just unbound, it's on a parabolic orbit, the eccentricity is exactly equal to 1. And if it's unbound, that means the sun can't hold it back, the eccentricity of the orbit is bigger than 1. So that's a hyperbolic orbit. So it's the shape of the orbit that is the key signature that is not from this solar system. And there's a bit of ambiguity because, when a comet, for example, falling in from the Oort cloud passes through the planetary region, the gravity of the planets can give it a little tug this way, a little tug that way, and it can change the eccentricity from slightly less than 1, so from a very, very extended elliptical orbit, to slightly bigger than 1, a very slightly hyperbolic orbit. And we do have a bunch of slightly hyperbolic long-period comets, which we are pretty sure come in from the Oort cloud and then get a little boost. It's kind of a gravitational slingshot, a little boost, and they go out a little bit faster than they came in, and then they're lost from the solar system. So there's a bit of a cutoff beyond which those gravitational kicks from the planets cannot explain the large eccentricity that we see. So Oumuamua is far above the eccentricity of any comet we've ever seen before. It's 1.3 or something like that, and those comets that get a little kick from the planets are like 1.03 at most.
Right. Okay. So like just a few fractions of a kilometer per second in increased velocity, and the comet isn't coming back, but there's no random collection of flybys of Jupiter and then Saturn, the grand tour in reverse to build up those kinds of slingshots for it to be able to be on that kind of a velocity. So it had to come from outside the solar system.
Correct. Yeah.
Yeah. And how did Borisov compare to Oumuamua?
Well, Borisov is another surprise in several different ways. First of all, it's a surprise to get, waited forever to get number 1. And then it's kind of a surprise to get number 2. So Oumuamua was 2017, Borisov 2019. But, Borisov looks like a comet. And so it's much more like the object that people expected to see before we saw Oumuamua. It has a coma, has a tail, and basically it looks like a solar system comet in every way, except that its orbit is even more ridiculous. The eccentricity is above 3. I mean, it's extremely hyperbolic, indicating that it's coming in with some huge excess velocity, bigger than it could ever get from any process in the solar system. So Borisov, if we found Borisov first, people would say, yeah, that's the way they are. That's the way they should be. But we found Oumuamua first. So a real big surprise is that we found these two things close together in time, but they look so different. They just look so different. And so it makes you wonder, have we found two completely different kinds of objects, just by coincidence at about the same time? Or is it possible that one is kind of an evolutionary product of the other? Like maybe Oumuamua came in as a comet-like thing with a coma and a tail, and then for some reason it lost it by the time that we detected Oumuamua.
And is part of it that we're seeing Oumuamua, like it was detected on its way out again. So we'd already missed its closest approach to the sun, and who knows what had happened to it before then.
Yeah, I mean that's an idea that I kind of like. There's no proof, of course, but there is room for the argument that Oumuamua being very, very small, so its effective, it's not a sphere, but its effective spherical radius is about 18 meters, so it's really small. There's an argument that it's small enough that it could have lost most of its volatiles, maybe even disintegrated on the way in, And as you say, it was detected only on the way out. So maybe we were detecting some remnant of something that was largely, but not entirely, degassed. And so it didn't look like a spectacular comet like Borisov, because we're seeing it on the way out. Now, Borisov also didn't come so close to the sun, and so it never was heated so strongly as was Oumuamua. And so it looked pretty much the same going out as it did coming in. So that's kind of an asymmetry between the objects. But we don't know. It's still entirely possible that that's not the case, and Oumuamua is just not the same kind of beast.
But having two objects to study is so much better than only having one, because now you can actually do some comparison and contrast. And so, when we look at Oumuamua and Borisov and then we compare them to the kinds of objects that we have in the solar system, I mean, do they have some, it's hard to explain. Do they have something that they share that's different from what we have in the solar system?
Do they have something that they share that's different
from us? Yeah. So only
the orbit.
Right.
Only the large eccentricity orbit. Yeah.
But in terms of composition, in terms of outgassing, in terms of motion,
we don't know the composition of Oumuamua because the damn thing didn't emit any gas, so we couldn't measure the composition. Now, Borisov, we could measure various gases that came out, and it looks pretty much like a solar system comet, maybe with a little bit more carbon monoxide than we would see in most comets in the solar system, but it's not extreme. It's not beyond the realm of solar system type body. So again, Borisov really kind of a not that surprising comet-like thing, albeit from another planetary system. But Oumuamua, we just don't have enough data to say. And I appreciate your comment about 2 versus 1, because the comment I usually get is about 1 versus 0.
Well, I mean, like when you think about, say, life on Earth, and we just have this N of 1. I mean, we don't know of any other examples of planets that have life on it, and so we just don't have anything that we can use to compare whether we're normal, whether we're unique, any of that. And so to have 2 now, there's some possibilities of interstellar meteors as well.
Oh yeah.
And maybe captured objects in the solar system that could have an interstellar origin. So, how far are you willing to take some of the speculation?
So the deal about interstellar meteors turns out to be surprisingly old. It's about 100 years old. So in fact, in the past, it was widely believed that all meteors are interstellar. I'm not quite sure why, but it was believed by there's a very famous guy, Opik, for example, who asserted that all meteors are hitting the atmosphere with this velocity faster than the escape speed from the solar system. They should all be hyperbolic. And he had measurements that he thought backed that up. And then there was kind of a battle between him and Fred Whipple, who is a very famous comet guy in the solar system. And Whipple won because it turns out the meteor, when you measure the speed of a meteor, it's less than the escape speed from the solar system. Now, that kind of battle continues. Most people accept that most meteors are from the solar system. They're pieces of comets, typically, and pieces of asteroids that hit the atmosphere. But there are occasional reports of bodies that come in with an eccentricity bigger than 1, speed greater than the escape speed. And then they would presumably be interstellar objects. The trouble is that when a meteor comes through the atmosphere, it's coming in at 20, 30 kilometers per second. It goes from some cosmic velocity down to like nothing over a distance comparable to the thickness of the atmosphere. The scale height is like 10 kilometers. And so it's all over in a second or a fraction of a second. So you have to measure the speed and the direction, with some significant accuracy in a very, very short amount of time. And it's very, very difficult to do that. So in general, when you see these claims of interstellar meteors, they're not substantiated. They're not actually believable because the uncertainties on the measurement are so big that you can allow solutions where they're not coming in on a hyperbolic orbit. So I would say at the moment there are no credible cases of interstellar meteors hitting the Earth's atmosphere. Unfortunately, true.
But as our detection methods, like I know astronomers are getting much better at tracking asteroids shortly before they strike the Earth, and in fact predicting precisely where they're going to be visible in the sky and produce a fireball and so on. So now we're starting to see objects that are a lot smaller that are moving, and that gives you everything you'll need to know if you actually spot one of those coming in 3 hours before it strikes the atmosphere.
Yeah, I mean, the future is always bright, so there's no reason to think that there are not interstellar meteors, right? I mean, if you got Oumuamua and Borisov coming in, presumably there's just some of the bigger objects in a size distribution that goes all the way down to very small bodies.
Yeah.
Because solar systems, planetary systems are just chucking out all of this stuff, and they don't care too much about the size of the things they eject. So yeah, interstellar space should be full of debris going all the way down to very tiny sizes. And then some of that should be hitting the Earth's atmosphere. But it's just the issue of detection. It's like, we think that's got to be true. And it wouldn't be at all surprising if we found these objects, but we haven't found those objects.
But have any recovered meteorites from the surface of the Earth, things found in Antarctica and stuff, have any of them had a chemical composition that the radiometric dating doesn't match the age of the solar system?
Right. I asked, I'm not a meteorite expert, but I asked meteorite experts here at UCLA to get the inside scoop on that. And they're like, nah.
Yeah.
No. So there's no evidence that we have interstellar meteors in the collection. And the truth is, maybe that will be a difficult thing to expect anyway, because since they come in so fast, they're much more prone to being detonated at high altitude. You get an airburst explosion. And so it'll be much harder for fragments to survive that. Now, I'm not talking about this thing by Avi Loeb in Harvard, who claims to have, found a meteor in the bottom of the ocean or something. There are claims out there. But in terms of reliable evidence, no, we don't have anything in a sample, in a museum or somewhere that evidently came from outside the solar system.
But we do see interstellar grains mixed in with the meteorites. So bits and pieces that maybe came from outside the solar system.
Yes, we do. And they've been incorporated in the bodies of asteroids that then fragmented and then came in.
Right.
And we also have measurements from spacecraft of very tiny interstellar dust particles that are able to penetrate into the solar system. So, and again, they're identified by their speed. They're coming in faster than the escape speed. They're typically very, very tiny. They're less than a micron, less than a thousandth of a millimeter in size. And they're mostly carried by what's called this helium stream. So there's a flow of interstellar gas that comes into the solar system, and it kind of brings these particles with it. And so they're well measured, and they've been well measured for a couple of decades. But no evidence for any of those particles coming into the Earth's atmosphere. The interstellar particles detected from spacecraft are too tiny to make meteors that we could see in the atmosphere.
But I wonder if some of the tiny pieces of dust on top of my roof are interstellar in origin. I'm fascinated by people who are going into old churches and stuff and running a magnet across them to pull off little bits of dust from space and then analyzing them under the microscope.
Yeah, I mean, I sure hope that's true. But
yeah. I'll let you know if we find one on my roof. Yeah. So let's talk about the source then. What do we think are the mechanisms that could be ejecting objects out of other solar systems to cross the gap to reach us?
So people have different ideas, but I think the most commonly accepted idea is based on what we think we know about the solar system. So we know that we have this Oort cloud of comets. We know that it has something like a trillion comets in it. And we know that the Oort cloud is so big, it's like 50,000 AUs in radius. It's so big that the comets could not have formed at those large distances. There was just no material in the disk around the sun going out that far. So they must have formed near the sun, and then they were kicked out. But the trouble is, when you kick something out from the planetary region, say between Jupiter and Neptune, when you kick it out, either it just leaves and goes off into the interstellar medium, or it falls back again to where it started if you didn't knock it out fast enough. So to capture it into the Oort cloud, you need a second perturbation. So you have to eject it with a kick from a planet, and then you have to disturb it again while it's going out to kind of circularize the orbit and lift the perihelion out of the planetary region. And we think that's done by the gravity of passing stars. But that's not a very efficient process. So the calculations suggest that only between 1 and 10% of objects launched out by the planets in the early days of the solar system were ever captured into the Oort cloud. And that means that if the Oort cloud's got 1 trillion things in it, then we lost 10 trillion or 100 trillion similar bodies to the interstellar medium. And that's just
and vice
star.
versa.
Pardon?
Yeah. And vice versa. Like all the other stars lost their version of that.
Yeah. So multiply 100 trillion by 100 billion stars, and you get a big number.
Right.
So that's the idea that people worked on and tried to do calculations with, like, well, how often should we see these things come back from interstellar space through the solar system? But that's a very difficult calculation because none of the numbers are that certain. But that's the basic idea. So the interstellar interloper population in that idea would consist of basically comets ejected from the disks around forming stars elsewhere in the galaxy, integrated over the lifetime of the galaxy. So they just chuck them out and they never come back. The galaxy is so distended, once you're launched into interstellar space, you never see a star again. You never hit a star again. You just float forever. The chance of hitting a star is effectively zero. And you very rarely even come close to a star. So probabilistically, Oumuamua and Borisov have never been so close to another star in their entire lifetimes in the interstellar medium, because the space between the stars is so huge compared to the size of a star. I mean, they're just out there. So we think that this is the interstellar population produced by generations of planetary systems forming at different places around the galaxy for the age of the galaxy, for the age of most of the universe, in fact. That's the prevalent idea. But if it's not that, maybe it's something like tidal shredding of a planet. So there's another idea that, if an asteroid passes too close to a massive star, to a white dwarf, for example, or a neutron star, or a black hole, then the gravitational shear at closest approach can rip it to bits, a bit like comet Shoemaker-Levy 9 that was ripped to bits by Jupiter back in 93 or 94. That could happen to, bigger bodies around stars elsewhere. And then you would send out this shower of fragments that, in principle, could escape and go off into interstellar space. So you can't rule that out. That is less rooted in what we know, because in general, when you shred a body, you tidally shred a body, it doesn't get ejected fast enough, doesn't necessarily get ejected fast enough to escape. A lot of that stuff is going to fall right back into the shredding object, which is what happened to Shoemaker-Levy 9. It didn't escape from Jupiter. It actually ended up just hitting Jupiter. So, the whole point is that we don't have much data. When we don't have much data, many things are possible. And then people who like to make models, make models. And they make a lot of models. And there are all sorts of possibilities that will have to be constrained by getting more of these things.
But there's like a difference between just an ongoing shedding of this material by every single star system out there. That would create a very large number compared to objects happening to stray too close to a compact object like a neutron star or a black hole. that sounds like it's not going to happen that often comparatively. And
That's what I,
so
yeah, that's what I
the
think.
number of objects that we should see will just give us an idea of which one of those is correct.
That's what I think. So I think that would be an unusual process compared to the one that we are pretty sure happened based on what we know about the Oort cloud. So I think that, provided other stars have Oort clouds, which we also don't know, then that should be a very copious source of these objects. And then shredding, yeah, I mean, maybe it happens, but maybe it's not the dominant source. The other issue with shredding, if you go near to a white dwarf or some other hot thing, that is going to be a thermal event that's going to lose a lot of volatiles. And then you would wonder, would a thing like Borisov even survive that event? Would this icy, carbon monoxide rich thing survive that kind of a shredding uh, event? And I think that's never really been explored, but I suspect the answer is no. So I kind of like the first explanation that these are just ejected comets that were not trapped in the Oort clouds of their own stars.
I mean, we do see hypervelocity stars in the Milky Way, and various ideas have been proposed for those interacting with the supermassive black hole at the heart of the Milky Way or being the partner of a supernova. And so you would imagine that any debris that was in the system when this event happened might also suffer a similar experience. And so you might get,
Yeah,
whatever's causing hypervelocity stars could also be creating interstellar objects.
yeah. And we see interstellar planets, of course. And, personally, I think the interstellar planets, so planets that are not obviously associated with any star, they're probably ejected from planetary systems in exactly the same way that comets are ejected from planetary system. So they get some gravitational slingshot from another planet that becomes more stable and they get ejected. And so I like that thought because that's a really nice way to think about this population of interstellar bodies that we're only dimly beginning to see right now. It probably goes all the way up to planet sized bodies, 10,000 kilometer sized things, Neptunes and Uranuses, and then all the way down to little bits of dust and stuff ejected from the disk of some forming star. And then we just happen to have lucked out to have seen, one eye and two eye, Oumuamua and Borisov, at about the same time that we're beginning to get a better handle on these interstellar planets. So it's kind of, it's not the nice thing about astronomy is it doesn't stop. You just keep learning more and more and more, and the picture becomes more and more clear.
So now that we know these things are out there, what efforts are being made to try to detect them with more regularity? What new instruments and telescopes are coming online that can maybe give us a better sense of what's coming at us?
Yeah, I mean the obvious answer is this LSST thing that will come up later this year. But there is a point to be made, which is that Oumuamua was discovered by an astronomical sky survey in Hawaii called PanSTARRS that is conducted for very definite scientific purposes, whereas Borisov was discovered by a guy amazingly named Borisov, who was just looking with his own homemade telescope near the sun just to see if he could see something, see a comet. And, that is very amazing. So it's testament to the excellence of that guy and his telescope and his dedication to looking at the sky near the sun. He didn't know what he found. He just thought, hey, it's a comet. And it turned out to be an interstellar comet, which is just a fantastic discovery. But the problem there is that we cannot use his discovery of Borisov to quantify the abundance of these interstellar interlopers because we don't know, and probably he doesn't know, the actual limiting magnitude or how faint did he go in his survey and over what area, for what time. So it's not a well quantified survey like the Pan-STARRS survey in Hawaii. So nobody's been able to use the detection of Borisov to understand the abundance of Borisov-like objects, whereas we have been able to do that with Oumuamua, giving rise to this idea that there's about one for every 10 cubic astronomical units of space. So what we need, to get around to answering your question, what we need is a telescope that does a systematic survey of the sky where the depth, the sensitivity is known, so we can kind of calculate how far away we can see these things, where the area of the sky that's looked at is well known, is quantified and published, and the duration of the survey is also well known. And then we'll be able to figure out, various things about the actual number of objects per unit volume and the number of objects as a function of size, the size distribution of these things over some range. And it looks like the LSST, Large Synoptic Survey Telescope, will be the one. So that's a big telescope in Chile that will come online later this year, supposedly, and will begin to do this all-sky Southern Hemisphere survey that will go on for 10 years, maybe longer, and will be a factor of several more sensitive than any survey yet done, and will cover, very large fraction of the sky repeatedly. So that will be, I think, kind of a killer app for finding 3i and 4i and 5i. And we have predictions for how many might be found. And again, they're all over the place, but they go up to, I think, 100 per year, and they go down to 1 or 2 per year. Those are the predictions.
And you mentioned this idea that there's maybe one per cubic 10 astronomical
one
units.
One every 10 cubic AUs. Yeah.
Right. And how many does that put in the solar system at any one time?
Yeah, so that's another thing that blew my mind about Oumuamua. So, the volume of the solar, if you represent the solar system as a sphere with a radius equal to Neptune's orbit, 30 AU, then the volume of that sphere is 100,000 cubic AUs, 10 to the 5 cubic AUs. And so if you go,
and that's just Neptune.
What? That's just Neptune.
And that's
that's inside the planet region. So if you got 1 every 10 cubic AUs, that means there are 10,000 inside the orbit of Neptune right now. And we detected just 1. And the other deal is that they're coming so fast that Oumuamua crossed from Neptune's orbit over there to Neptune's orbit over there, went right across the planetary region in 10 years. So you've got 10,000 things crossing the solar system in 10 years. That means it's 1,000 per year. So we have 1,000 of these objects coming into the solar system and then another 1,000 leaving every year. So that just gives you an idea of the incredible population of interstellar interlopers implied by the detection of just the first one, Oumuamua. So that's why we want to get better statistics so we can see, is that right? I mean, that's just incredible.
And so the problem is that because Borisov was an amateur out there with their telescope and they happened to spot it, as opposed to a comprehensive survey that was watching a chunk of the sky waiting for the very first moment that one of these objects was detectable. If the same thing had been used to discover Borisov, then we would have dramatically greater accuracy in terms of how many of these things are passing through the solar system.
Yeah. And we'd have a little bit of a handle as well on the size distribution because Borisov is bigger than Oumuamua. Borisov is somewhere between 200 and 500 meters. My guess is 400 meters in radius, effective radius, compared with Oumuamua, which was just 80. So it's a factor of 5 or something in radius. And so that would give you something about the size distribution as well. So we'll get that. We should get that from LSST and other survey telescopes that do a good job and a systematic job in looking at the sky. There's another one that's going to be launched, I think 2027, called the Eneos Surveyor. So that's a telescope that is designed to look for near-Earth objects that might one day hit the Earth. But it will find all sorts of stuff, and it will find anything near the Earth, whether it's going to hit us or not. And that will include interstellar interlopers, I think. So the future is bright. We've got these new facilities. They're going to find stuff. And we just have to wait for those facilities to begin to work.
Yeah. So, we think about the incredible velocities that these things are moving through the solar system, and yet there is a dedicated dedicated team of dreamers who think that maybe we could chase these things down. And I don't know if you've been watching the efforts of the Project Lyra group as they continue to propose different launch vehicles and different trajectories.
Uh-huh.
How much of a priority do you think we could and should put on trying to do at least a flyby of an interstellar object, if
Well, I
not a
mean,
sample
it's
return?
yeah. I mean, it's obviously exciting to try to do that, but it's also extremely difficult, right? So
Yeah.
the truth is, we have trouble reaching even most things in the solar system with our existing rocket technology. So you'd have to be very lucky to do that. What would be the reason for doing that? Well, you could do a lot of measurements that you can't do from the ground. So, for example, if you could carry some kind of a mass spectrometer to the object, you could do incredible measurements, not just like blunt force measurements of how much water is coming out and how much CO is coming out. You could measure the isotope ratios in these things and then compare them with objects in the solar system, with the Earth, with the comets, and so on. You could do a whole bunch of scientific measurements that you can't do remotely from a telescope. So that would be very exciting. And then the most, how can I say it, the most optimistic people even hope to bring back a sample.
Mhm. Yeah. Yeah.
And
I
that,
interviewed somebody on this, and they were thinking that you could like bolt an ion engine onto a fission reactor, and then that should get you hundreds of kilometers per second in delta V. And that's enough to chase down Oumuamua, grab a sample, and bring it back home for study here on Earth.
well, good luck with that. I mean, that
Yeah.
would be that would be great.
Yes,
So
please.
that's all I'm going to say about that. I mean, that would be just awesome. It's good to think big, of course,
Yeah.
but I think we're not going to see that anytime soon. Not least because we don't have any targets to go to look at, but B, when we do, we'll probably know about them only shortly before they pass through. And so there's this timing problem. You have to get the rocket there in a very short amount of time because we don't see these things until they come very close because they tend to be small. And in addition, we just don't have the kinds of technology that is being talked about to do these missions. But yeah, as an objective, that will be wonderful for sure.
And this is going to be more speculative, and feel free to dodge the question if you want. But one of the ideas of the source of life on Earth is panspermia, that life has been shifting from world to world.
Oh, yeah.
If we ever find a common ancestor on Mars, we find life on Mars, we detect a common ancestor, then there had to be some mechanism that was getting life back and forth from Earth to Mars. We have Mars meteorites here, and so like that explains it. But if there is 10 times as much material traveling from star system to star system, you know, does it seem unlikely that now maybe there's organic material, maybe even life being passed along from star system to star system?
I think it's possible. Interplanetary panspermia looks like it's really possible, right? So we have a mechanism, you impact a planet, you blow out boulders, rocks, and they fly around, they hit another planet, and those boulders can preserve um, bacteria. We know that from experiments, even. We know that. They can survive that kind of interplanetary journey. So that's a plausible process. Whether it occurred or not, whether it's related to life on the Earth, we don't know, but eventually we might know. Interstellar panspermia, much more difficult. So actually the flux of material, the mass of material per unit time hitting the Earth from an interstellar origin is, I think, 10,000 times less than the flux of interplanetary material. So most of the stuff that hits the Earth is from something in the solar system, typically an asteroid. And very little is from any interstellar source, based on what we know essentially from Oumuamua. So in the last 100 million years, we were hit by a 10-kilometer body that caused this massive KT extinction, 10 kilometers. But in that same time, we probably were hit by only one Oumuamua-sized body. So it's 80 meters compared with 10 kilometers, 10,000 meters. And so it's just a huge mass of interplanetary stuff compared to interstellar stuff. So we don't really expect to find impact craters caused by interstellar bodies. And as I said, we haven't found meteorites so far that we can identify as being interstellar in origin. The flux is just way, way lower. So for that reason alone, I think it's much more difficult to imagine that kind of interstellar panspermia.
But with this sort of age of interstellar objects, as well as this age of rogue planets, do you feel like it's starting to kind of change your perspective on what the Milky Way contains and sort of what's out there?
Oh yeah, well, it's changed my perspective. My perspective is that we don't even know what's in the solar system, right?
Yeah. Yeah.
I mean,
if there's 10,000 within the orbit of Neptune, where are they?
It's just, the whole thing is just insane. So you get the idea because you listen to NASA and, oh yeah, we're going to Mars and everything is well known. Okay, fine. But you go beyond Jupiter or something, the solar system is not really well known at all. Kuiper Belt was unknown, right, until very recently. That is a region, it's like 1,000 times the mass of the asteroid belt. 1,000 times. There's 1,000 Kuiper Belt objects for every asteroid of the same size. And we didn't even know about that until yesterday, essentially. And that's not even that far away. Think about what's beyond that. What's beyond that? And then how do we know anything about the Oort cloud? Only because a few objects from the Oort cloud have been knocked in by the gravity of passing stars. So there's enough room in the outer solar system for almost anything you want. The question is it really there? So you have these people talking, oh yeah, we found a planet in the outer solar system, but they haven't actually come up with that planet yet. Like, where's the beef? You got to have the evidence. So I think the possibilities are almost endless. It would be a huge mistake to think that we know even what's in the solar system, let alone what's in the galaxy. But it has to be evidence-based all the way. Otherwise, it's just BS.
Yep. Yeah. Yeah. I love this idea that there are these objects free floating, that we think about the closest star or maybe the closest planet being Proxima Centauri b to the solar system, and yet in fact, depending on where the estimates stand, there could be dozens of objects between us and that distance. We just can't see them, and they're just free floating in space, drifting around.
Yeah,
we just
find the easy stuff, basically.
yeah, the stuff under the streetlights, right?
Yeah.
To use the analogy.
Yeah, for sure.
So I want to shift gears a little bit. A lot of the conversation that we're having is based on a textbook that you're working on, which is sort of in pre-release. But you are also working on active asteroids research. So can you explain what that is?
Yeah. So the idea used to be that asteroids are rocks, essentially, and they're rocks because they formed near the sun at high temperatures. And at high temperatures, you can't trap water ice because water is steam. It's a gas. It's steam, and it doesn't freeze out. Whereas beyond this critical distance, maybe 4 or 5 AU, something like that, temperatures are low enough that ice can freeze out. And so things that form far from the sun contain ice. Things that form near the sun don't. So asteroids are rocky because they form near the sun. Comets are icy because they formed far away. So starting about 15 years ago, Henry Shea, my former grad student in Hawaii, who's still in Hawaii, and I established that actually there's a population of intermediate bodies that look like asteroids. Their orbits are like asteroid-type orbits. They go around pretty circular orbits in the right place in the solar system. But they have the physical appearance of comets. They're ejecting material. They're ejecting dust. And in some cases, they're ejecting gas. So we called them, first we called them main belt comets. And then a whole bunch of asteroid people got angry with that. And then we called them active asteroids, and a whole bunch of comet people. So people are angry, but we call them now active asteroids because they are asteroids and they are active. You can't argue with either of those things. And the question is, what causes the activity? Because why would a rock just be ejecting material? That you go into your backyard and the rocks in the backyard are not spewing out stuff. They're
Right.
rocks.
Right. They're desiccated already.
Yeah,
And so any gas
is that weird? So
yeah.
so I've done a lot of measurements and a lot of thinking about this, and have identified a whole bunch of different processes that can cause an asteroid to lose mass, to eject stuff. So the first one that we suspected was the explanation for what we saw is that indeed the asteroids contain ice. But the puzzle there is the asteroids are pretty hot, and ice cannot survive at the temperatures that we find in the asteroid belt because it just sublimates away on a timescale of 1,000 years or something, much, much less than the age of the solar system. So the resolution of that seems to be that the ice is buried below a layer of regolith, below a layer of rocky debris. And then sometimes caused by micrometeorite impact. And then sometimes you have a bigger impact, it disturbs that layer, it exposes the ice, and the ice sublimates through the hole, and it makes the asteroid look like a comet until that is kind of a wound. That wound will then scab over, and the sublimation will stop. So we have identified a population of icy asteroids, mostly in the outer parts of the asteroid belt. And you could say, well, who cares? That is a region from which the Earth is widely suspected to have acquired its oceans, for example. So there's this question, where does the water come from? Where do the volatiles come from? There's a pretty good linkage to the outer parts of the asteroid belt. So we may be seeing the region from which the Earth's and other terrestrial planet volatiles were delivered, which is kind of interesting. And it means if you can go there with a spacecraft, as the Chinese are now planning to do, you'll be able to measure basically the physical and chemical properties of primordial ice in the solar system.
I didn't realize. So they're planning with their asteroid mission. They're planning to go to an active asteroid.
Yeah.
Oh, I didn't know that. Okay.
Yeah. I think they're going to. It's called 311P.
And so when we think about, say, the traditional explanation for where the Earth got its water, the idea is comets, that you've got comets that are coming from the outer solar system and they're smashing in. But the rate of cometary impact compared to the rate of asteroid impact is a fraction.
Correct.
And so, we can thank Jupiter for hurling, shoving giant chunks of the asteroid belt in our general direction. And so if a lot of those contain a lot of water left over from the formation of the solar system, then that would be a more efficient mechanism for getting water to the early Earth. Is that sort of what you're proposing?
Well, there are different arguments, right? But it used to be, as you said, it used to be thought that comets must be the source because comets are icy, so that's where the water comes from. The rate of impact is a problem, so it doesn't seem the comets have a sufficient rate of impact to supply the oceans. Maybe in the early times you could arrange for that to change, but it doesn't seem likely. And then many measurements of the deuterium-hydrogen ratio in comets were obtained in the last 20 years or something, and those D to H ratios in general are not the same as what we see in the oceans. So if you just melted a comet, you would have a different D to H ratio from the one we observe. So the tide has turned, slight pun there, but the tide has turned against comets as the preferred explanation. We do know that we are frequently hit by debris from the asteroid belt. We have all these meteors and things coming in. So we know there's a dynamical pathway from the asteroid belt to the Earth. And we do know also that the asteroids, the outer belt asteroids in particular, contain volatile materials. Now we know that there are icy objects there. And so it's very, very natural to think that that's a place where the Earth acquired its volatiles. And the idea being that the Earth formed really hot, had this molten surface, not suitable for the trapping or preservation of water or other volatiles. And so the volatiles are thought to have been dumped afterwards, later on, in what's called a late veneer. Now, this is a very messy subject, much more messy than many people thought it would be. My guess is the Earth oceans have a whole bunch of different sources, including some contribution from the comets, but not a dominant one, some contribution from the asteroids, possibly a dominant one, and maybe even some primordial water that got into the Earth and then has been outgassed through the volcanoes and so on. So multiple sources are probably responsible for what we have on the Earth, but the asteroids are part of that. And then some of these active asteroids look like they're implicated because they've got ice and they're in the right place in the solar system. So that's just one kind of active asteroid. There are other kinds. So we have seen collisions between asteroids that briefly produce an expanding cloud of debris. First one was seen in 2010, and that was a big surprise because the expectation is the timescales for these collisions are so long we'll never see one. We have no chance of seeing a collision in our lifetime. And it's true. For the first object we saw, the collision timescale is something like 10 million years. But when you think about it, so you have to wait for 10 million years to see this impact. So we have no chance. But there are 10 million asteroids like that. And so it's not that remarkable that we would see one. So everything kind of clicked at that time. Oh, yeah, we can see them, and we've seen a bunch of those since. And then to me, even more fascinating, we see this thing called rotational disruption. So it turns out if you put a rock in space and shine a light on it and do nothing else and just wait, that rock will begin to spin. So the momentum from the photons will cause the body to spin up. And that's true for asteroids, and it's true for little rocks as well. So for asteroids, it takes probably tens of millions of years, depending on the size. But that, again, that's short compared to the age of the solar system. The only thing that we can think of that limits that spin up of the asteroids by radiation torque, as it's called, is breakup. So we think that most asteroids are rubble piles, like a bunch of grapes, where the grapes are held together by very weak forces, by gravity and maybe weak electrostatic forces like Van der Waals force. If you spin them, they're just going to break apart. And we have seen that several times, several different objects in the asteroid belt. So these active asteroids turn out to have multiple explanations. There turn out to be many reasons why some boring old rock in the asteroid belt can suddenly look like a comet and eject material. And it's all kind of fascinating because it's all kind of new. And then, with regard to that spin-up thing, the rotational disruption of asteroids, we always used to think that the asteroids are just this population of bodies that kind of started big and they smash into each other and make fragments, and then the fragments smash and they get smaller and smaller and smaller and they pulverize all the way down to dust. Now it turns out that when you get down to the kilometer-sized asteroids, the dominant destruction mechanism is this rotational breakup under the action of torques from solar radiation. So it's collisional all the way down, but then when you get to 1 kilometer asteroids, of which there's a million, then suddenly it becomes faster, more efficient for them to spin up and explode than it does for them to be collisionally smashed and shattered.
Oh, that's really interesting. And so the smaller, when we see these asteroids that all came from some larger object in the past, instead of there being some collision that was the cause, in fact, it's just the sun, the light pressure spun them up until they shattered.
It's collisions all the way down, and then when they get to be a kilometer or smaller than that, then it's the rotational breakup that's faster. So the production of dust for the zodiacal, the asteroid part of the zodiacal cloud, the production of meteor streams from disrupted asteroids probably originates that way by this rotational breakup. And then that's also plugged into what we found recently from spacecraft, which is that, certain asteroids have this weird diamond shape where the equator is wider than the poles. And, it's literally like that kind of shape. It's like it's flat here and flat here going down. It's got this fat equator. That is due probably to material that slid from the polar regions down towards the equator,
Right.
giving this big ridge around the equator. If they spin a little bit faster, that ridge will be unstable. It will fall off. And that will create the kinds of objects that we've seen in some of the active
Like you
asteroids.
get a ring. Like these things will just start to have enough escape velocity. They'll just start to just lift off the surface of this asteroid, go into orbit, and then maybe land again on a part that has a higher gravity. I know they can sort of shift around, almost like they're jumping off of the surface of the asteroid and then
Right.
landing
So,
in different spots.
yes. So exactly. So people have simulated that with numerical models. A lot of that stuff, the debris just rains back on the surface. Sometimes it escapes. Sometimes it makes a satellite, a moon. And so that is presently the preferred explanation for the high abundance of little asteroids with moons, which again was something that we had no idea about a few decades ago. In fact, there were many, many clear, explicit papers saying there's no way an asteroid can have a moon.
Right. Right. Because you
And
can't
they're
like
everywhere.
capture it or whatever, but if
No
in fact they're
gravity,
just
there's no way, but they're
yeah,
everywhere.
that's really interesting.
Yeah.
Yeah, fantastic. Well, David, what are you obsessed with right now?
I'm still obsessed by the interstellar interlopers. I really am. So I'm desperately waiting for the third one, 3I, as we're
Yeah.
calling it, even before it's discovered.
Right. It's already got a designation. Just need
Yeah,
to wait for the
because
object.
because there are so many questions raised, basically by Oumuamua, like why did Oumuamua have that strange shape? Uh, why did it have this strange motion? Has this non gravitational motion? Why is it like that? And why is it different from Borisov? None of these questions are going to be answered by anybody's theory because there's no theory, and none of them will be answered by any model because there are no there are models, but there are no constrained models. You can only answer these kinds of things with data. So data is what I do. I'm very interested in observations, and I'm very interested in observing the next few interstellar objects until that population becomes better understood, better characterized, and then I'll be interested in something else after that.
Right. Right. And when that mystery is better solved, then you'll lose interest and move
Yeah,
on to
I mean
something else.
the good thing is that with these new facilities, with the LSST survey telescope, and maybe the NEO surveyor infrared telescope in space, we'll make discoveries. So the whole deal is not just working on things that you know, but the real excitement is working on things that you don't know. So we'll find stuff that we haven't even imagined yet.
Yeah. I think about like with Vera Rubin, you think about how we know of about 1,500 Type 1a supernova right now. And in theory, over that 10-year process, it'll find millions. Like we're looking at orders of magnitude discovery of all of the things that we're familiar with.
Right.
So
But
whatever you know of right now, enjoy a
yeah,
hundred times as many.
yeah, it also means that all the work that I did will just be replaced in like 6 months,
Right. Yeah.
which is good in a kind of
Yeah.
a sad way. But what it really means is, new observational capability gives you the chance to discover something completely unexpected.
Yeah.
That's the excitement for me.
Yeah, for sure. I mean, that it's not seeing the stuff that we were expecting. It's that's unusual.
Yeah.
What's the cause of that? I mean, the most recent example that I think is when I think about like fast radio bursts.
Uh-huh.
Something that just came out of nowhere that no one was expecting. No one ordered it up, and yet there it was. And now it's mostly solved, but still,
Yeah.
it's great to see something just come out of nowhere and show that the universe can do things that we hadn't even thought of.
Yeah. And I like that because it's kind of opposite to the view that I was given when I was a preteen, a million years ago, which is kind of a boring thing like, oh, yeah, the science has theories and the theories make predictions and then observers just confirm the predictions. That's absolutely not the way it works at all.
Right.
Not in astronomy, for sure. It's like, oh my God, we found a new thing. We've made this discovery. We don't know what it is. And then everybody and his dog comes in with an idea, with a model to try to explain that. That is much more exciting than the old model
Yeah.
that I was told.
Yeah, 100%. Totally agree with you. Well, David, thank you so much for taking the time to chat with me today. Good luck on the search for I3 and I4 and then I-10,000. 3I, right? 3I. Yeah, 4I and all the others.
Yeah.
Thanks a lot.
Thank you.
I hope you enjoyed this interview with Dr. David Jewitt. I'm going to give you some of my thoughts and impressions in a second, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Adam Schaefer, Andrew M. Gross, Bill, David Giltonan, David Matz, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modzo, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Shepelin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. Like many people, I didn't ever expect that we would detect an actual interstellar object passing through the solar system. It didn't seem like there were a lot of mechanisms that would allow these objects to escape from one solar system and pass through the cosmos. And yet now we know there are more. And that point in the interview where David says, no, there could be 10,000 just within the orbit of Neptune. Just think how many could be all the way out into the Oort cloud. Like there could be a lot of these objects in the solar system, a lot of these objects passing from place to place throughout the Milky Way. And so this is just an incredible opportunity for us to study the composition, the environments of other star systems out there across the galaxy in a way that we could just never do up close. And there have been a lot of really interesting proposals to chase these things down, to do even just a flyby, to do a orbiter, to do a sample return, and just imagine what we could learn by having a sample like, say, OSIRIS-REx or Stardust or from Hayabusa 2, one of these samples brought from an interstellar object and brought back home to Earth. And as we wait for Vera Rubin to come online later this year, early next year, we really are just at this quiet time, this quiet before the storm, when we will start to find dozens, if not hundreds, if not thousands of these objects passing through the solar system that were all around us and we just never noticed. All right. Hope you enjoyed this. We'll see you next time.